Hello and welcome. If you want to see attractive animated tutorials like this one, visit algopk.com. Today, we're learning about stacks, one of the most important data structures in computer science. What is a stack? Imagine a stack of plates in a cafeteria. You can only add a new plate on top. You can only remove the plate from the top. You cannot pull a plate from the middle or bottom. That's exactly how a stack works in programming. We call this LIFO, L-I-F-O, last in, first out. The last element you add is the first one you remove. Look at the animation. When we push elements, they stack on top of each other. When we pop, we always remove from the top, never from the middle, never from the bottom. Stack operations. A stack has four main operations. Let me explain each one. First, push. This adds an element to the top of the stack. Watch the animation. The new element appears at the top. The top pointer moves up to point to this new element. Second, pop. This removes the top element from the stack. Watch the animation. The top element disappears. The top pointer moves down to the element below. If we try to pop from an empty stack, we get an error called stack underflow. Third, peek. This lets us see the top element without removing it. The element stays in place. We just look at its value. Fourth, is empty. This checks if the stack has any elements. It returns true if the stack is empty, false otherwise. How stack works in memory. Let's look at how stacks are stored in memory using linked list implementation. Each element in the stack is a node. Each node has two parts, the data, which is the value we store, and a next pointer, which points to the node below it. The top pointer always points to the most recently added node. When we push, we create a new node and link it to the current top. Then we update top to point to the new node. When we pop, we save the top node's value, move top to the next node, and remove the old top node. Now it's disconnected and can be freed from memory. Time complexity, all O of 1. Here's the beautiful thing about stacks. All operations are O of 1, constant time. Push is O of 1. We just add at the top, no traversal needed. Pop is O of 1. We just remove from the top, no traversal needed. Peek is O of 1. We just look at the top, no traversal needed. Is empty is O of 1. We just check if top is null, no traversal needed. This makes stacks extremely efficient for their intended purpose. Push operation step by step. Let me walk you through push in detail. Watch the animation carefully. Step 1, we create a new node with our value. The node gets a memory address. Step 2, we set the new node's next pointer to the current top. This links it to the stack. Step 3, we update the top pointer to point to our new node. Now it's officially the top of the stack. 3 simple steps, constant time. That's the power of stacks. Pop operation step by step. Now let's understand pop. Watch the animation. Step 1, we check if the stack is empty. If top is null, we cannot pop. That would cause stack underflow. Step 2, we save the value of the top node. We'll return this later. Step 3, we move top to point to the next node below. Step 4, we return the saved value. The old top node is now disconnected and can be freed from memory. Real-world applications. Stacks are everywhere in computing. Function calls use a call stack. When function A calls function B, A goes on the stack. When B finishes, we pop back to A. This is how recursion works. Undo and redo in text editors. Every action goes on a stack. Press undo, we pop the last action and reverse it. Browser back button. Every page you visit goes on a stack. Click Back, we pop the current page and show the previous one. Expression evaluation. Compilers use stacks to evaluate mathematical expressions and check if parentheses are balanced. Backtracking algorithms. Solving mazes, puzzles, and games often use stacks to remember previous states. Common mistakes. Let me warn you about common errors with stacks. First, stack underflow. Always check if the stack is empty before calling pop or peek. Popping from an empty stack crashes your program. Second, stack overflow. If you keep pushing without popping, you'll run out of memory. This often happens with infinite recursion. Third, forgetting to update top. When pushing or popping, always update the top pointer. Missing this step breaks your stack. Fourth, memory leaks. In languages like C and C++, remember to free the memory of popped nodes. Stack versus array. You might ask, why use a stack when we have arrays? Arrays allow random access. You can access any element by index. Stacks restrict you to only the top element. But this restriction is the strength. It enforces LIFO order. It makes your code clearer. When someone sees a stack, they immediately understand the intended behavior. Use stacks when you need LIFO ordering. Use arrays when you need random access. That's stacks explained simply. Remember LIFO, last in, first out. Push adds to top, pop removes from top. All operations are O of 1. Practice the push and pop animations. Watch how the top pointer moves. See how nodes link together. For more attractive animated tutorials on data structures and algorithms, visit algopk.com. See you in the next lesson.